Okay, and again, make sure you do put here in the chat box there. Thank you. Okay, so as I mentioned earlier in lecture there, I'm going to finish up at least this part about nomenclature. Again, I know next week's lab is about maybe nomenclature and some Lewis structures. We'll get into the bonding and Lewis structures on Monday for sure. And maybe we'll see where we're at here at the end of the discussion. So that's the game plan. We're going to kind of pick up here where we left off in lecture. And again, hopefully that'll be helpful for you as you kind of approach your lab for next week as well. All right, let me do that. Let me do this and do that, I think. Okay, so we've been talking about nomenclature, or we started talking about nomenclature, and again, a couple of things. As I mentioned earlier, if you do have an ion by itself, so if you're asked to write sort of the formula for a cation, it should include a charge. So for example, here, the cation in the example we did above would be lead with a +4 charge there, and that would again be our cation. And in this case, because it's one of those sort of guys that can have a variety of charges, what we would want to do is, if we were actually going to name this ion, it would be the lead Roman numeral 4 ion. And again, as I mentioned, very, very often kind of confused or messed up upon. The Roman numeral is not how many we have, but it is simply if you took one of those positive guys out, what the positive charge would be on it. So again, that's why we would include the Roman numeral 4 here for that reason. Now, if we had a cation like we had earlier, like say the Na plus, again, we would include the plus, but we would just call it the sodium ion. Again, we don't have to specify the charge there because it's a type 1 compound or ion, and it basically has a fixed charge. Different than lead. Lead could be +2, +4, and so forth. So because it has a wide variety of charges it could be, we have to basically tell people, hey, in this case, we're dealing with the +4 version of lead. So that's why we have to include it in our name. If you're asked to sort of write the formula for the anion, it would look like this: oxygen with a -2 charge, not both of them, just one. And again, if we were to name that guy, that is our negative ion, so it gets the IDE treatment at the end. And again, that's how we get to the oxide name there. So whenever we do put a positive and negative together, as we mentioned a couple of times earlier as well, we always want to make sure that we end up with no overall charge. And again, the other really important thing of that is what I mentioned a number of times. When you do put it together, it needs to be the simplest way that you can put those things together to get yourself a zero charge. So in the case of this last example that we did, the simplest way we could do it is with one lead with a +4 charge. We needed a couple of these guys basically to balance it out. Any questions on that we talked about? Again, both of these guys are ionic compounds, which means there's absolutely positively no sharing of electrons happening here. We have a complete transfer of electrons. And what's holding all these guys together is simply that positive and negative attractive force between those two. Now, there is sort of an older school way of naming guys with charges, with sort of a variety of charges, where they kind of use the root of the name and either ends in ic or us. So instead of iron 3, we would call this would be called the ferric ion. Instead of iron 2, this would be the ferrous ion. Personally, we're not going to use any of those names, but you should be aware of it. It sometimes pops up occasionally, that kind of older way of naming. For us in here, we will use the Roman numeral way of naming. And again, that's the way you should name things that need Roman numerals, not so much the old school way. So don't use the old school way. Use the Roman numeral way for our type 2 guys. And again, type 1 guys do not need a Roman numeral because they basically possess that fixed charge, which means you don't have to worry about telling people what you're dealing with because it's known that that guy can only make one type of charge. Any questions on that there? Okay. So here's a table from your book again of some of our Roman numerals. You can see this is a +3, so we got a Roman numeral 3, Roman numeral 5 for 5, and so forth. So all these guys have the ability to make multiple types of charges depending on who they sort of bond with and how many. So we do need to include the Roman numeral. One really odd one is Mercury. Oddly, when you look at Mercury that has a lot of 2s in it, it's actually Mercury 1. While if you look at Mercury that has like only 1 2, it's actually Mercury 2. So Mercury is kind of a weird one. It's because this guy is really kind of 2 Mercury 1s together. It's what's sometimes referred to as a dimer, which is why there's a 2 on the bottom, because it's actually 2 individual Mercury 1s that are kind of bound together, and that's sort of how it comes. So oddly, the one with the most 2s in Mercury's case is actually the one that's Mercury 1, and the one with just the 1 2 on top is Mercury 2. How would you know the difference? Because that extra 2 will find its way into the formula, and you'll be able to sort of recognize it that way. Again, if you do come across something with Mercury sort of in it. So all these guys are really type 2 metals. And really, when we're talking about type 2 metals, we are really looking at the transition metals. And again, just to the right on the periodic table below the staircase, the only 3 exceptions from that transition metals that we talked about earlier, that's zinc, which is always a +2, cadmium, which is a +2 always, and silver. So those are 3 exceptions that are actually type 1 guys. They have fixed charges. So even though they're transition metals, that is some exceptions that occur there. So we touched upon this a second ago at the end there, but when we go to really name these guys, pretty straightforward, just like type 1. Again, we're going to use that whole name of the metal. We're going to do that non-metal with the IDE at the end of it. And again, no matter how many non-metals we have at the end, will have no effect on the name. We just name it that way. And again, the one thing that you need to do there with our type 2 is include that Roman numeral, which again is the charge on the metal. And that obviously is the positive charge that's on the metal. Just like before, positive guy first, negative guy second, both name and formula when we do it. So why don't you give a few a try here and see what you come up with. So you have, I think, on your list there, you have COCl3, you have CUI, you have SNBr4. And while you're at it, let's make sure we could go the other way as well. Why don't you write the formula for iron 3? Iron 3, let's do actually bromide. Why don't you do lead 2 phosphide? And why don't you do, let's do nickel 4, and let's do oxide. All right, guys on the left, we want the proper name. Guys on the right, we would like the proper formula. So take a couple minutes or so, see what you come up with. We'll make sure hopefully everybody's on the same page here. Take a look and sort of see how we're doing here. All right, so looking at the first one here, again, you want to approach it kind of the same way as we've done before. if you're not sure where to start, you just kind of want to identify what things are. So CO's cobalt, that is a metal. Cl is chlorine, which is a nonmetal. So automatically that should tell you it's an ionic compound. So whenever you're dealing with an ionic compound that's a metal and a nonmetal, as we talked about, it is always the metal which is the most important part. So the next step you would want to do is go look at the periodic table and try to find where you can find cobalt. And if you're not sure, if you look at the periodic table there, cobalt should be like number 27, dead on center almost, I think, of the transition metals. So as soon as you see that, that also should indicate to you that cobalt is a type 2 compound because it can have multiple charges. So what that means is, again, at this point, we may not know what the charge is on the cobalt, but the good news is we do know what the charge is on the Cl. Cl is over here in group 7 on the periodic table. And because it's in group 7 on the periodic table, we know that Cl basically carries a -1 charge. Now, there's not just one Cl present. Based on that, there is a grand total of 3 of these Cl minuses present. And that's important because if we add up all that negative charge, that is a negative charge of -3. So what we talked about was that the metal and the nonmetal should always equal 0 when they come together. That means that we know that since there's only one cobalt present, it does need to carry a +3 charge. Any questions on that so far? That means that when we go to name this, we do use the whole name of the metal, which is cobalt. Because cobalt's a transition metal and can have multiple charges, we do need to include a Roman numeral, which in this case is Roman numeral 3, not for how many cobalts we have, but for the actual positive charge that is present. Just like type 1 and type 2, regardless of the fact that there are 3 Cl minuses, it has no effect on the name, and it would be chloride. So this would be cobalt, Roman numeral 3, chloride. Any questions on that there? Coming down to the next one, we see Cu, which again is a metal. I, which is a non-metal. Again, the metal being the most important one here. It also is a transition metal, a couple doors down there from cobalt. And because it's transition metal, again, the same logical reasoning that we just talked about would come into play. That means copper can have multiple charges. Good news is we will know what the charge is on the I. I is group 7, which means it has a -1 charge. And there's only one of them, which means to balance it out, the copper here would have a +1 charge. Thus, we use the whole name of the metal, which is copper, Roman numeral 1, again, for the actual charge on the individual copper metal. And iodine becomes iodide, IDE at the end of it. Any questions on that particular one there? Rolling this way, we see SN, which is tin. And again, if you look for tin on the periodic table, it's not necessarily really part of the transition metals. It's actually found kind of like in this area, kind of below the staircase here. And some of those guys below the staircase, which are metals like tin, lead, bismuth, antimony, those guys, they also have a variety of charges or variable charges. So they are treated very much like transition metals, which means I'm not sure what the charge is. So again, we're going to look over here at our Br. Br being group 7 means it has a -1 charge. Again, there are 4 of them, which means we just can literally draw it out to add up everything if you like. That is a grand total of -4, which means to balance it out here, the tin should be plus 4, and this would be tin Roman numeral 4, again for the charge, not how many. And because we have 4 of the bromines there, has no effect on the name other than we do need to make it IDE at the end of it there. It's just an I there. And that would be tin Roman numeral 4 bromide. Any questions on any part of those names there? All right. Again, when you have the names and you're working backwards, you want to kind of just think about the individual pieces that make this guy up and then put them together correctly. So when I see iron Roman numeral 3, a couple of things come to mind. First off, I see a Roman numeral, which tells me it is a type 2 compound. But even better is when I see a Roman numeral, it also tells me what the charge is. So if it is, if your question is, will they always have Roman numerals? They will if it's a type 2 compound. And a type 2 compound is what we're talking about here. This is a metal and a non-metal. And if you have a metal and a non-metal, and it's always the metal that's important in that situation, if that metal comes from the transition metal region of the periodic table or just to the right of the transition metal region, what that essentially means, things like lead, tin, and all those transition metals, other than zinc, cadmium, and silver, what that means is those guys can have a variety of charges. So like copper could be +1 or +2, iron could be +3 or +2. So you do need to include a Roman numeral, and basically the Roman numeral is just telling people in this particular case, I'm talking about the iron that has a +3 charge, rather than if I had iron 2 chloride, I'm talking about the iron with a +2 charge. If it's a type 1 compound, which is basically the same situation here, which is also a metal and non-metal. Again, the metal here would be group 1, 2, 3, or silver, zinc, or cadmium. They do not need a Roman numeral because they have fixed charges. So no matter what the situation is, they always have the same charge no matter the situation. So these guys always need the Roman numerals. These guys never need Roman numerals. So it is specific for this type of compound. You're welcome. Other questions on that? Okay, so coming back with our name, when I do see that Roman numeral there, so the fixed charges, this is what we talked about earlier. So let me just let me back up a page so I can have somewhere to scribble on here. So when you look at the periodic table, group 1, group 2, group 3, 4, 5, 6, 7, and 8. Everybody in group 1 will make a +1 charge no matter what the situation. They have a fixed charge. Everybody in group 2, when they do make a charge, will have a +2 charge. Group 3, and usually here we're talking about aluminum, will have a +3 charge. Right around here is that staircase that kind of comes down where we have our semi-metals. Skipping group 4, but going to group 5, the non-metals, because they will gain electrons, will have a -3 charge. The group 6 will be a -2 charge to non-metals, and group 7 will be a -1 charge. So it's kind of +1, +2, +3, skip 4, and then go backwards on top there, -3, -2, -1. 8, which is the noble gases, no charge because they're noble gases. Now, when we talk about the transition metal region, which is in this area here, our transition metals, they have a variety of charges or variable charges. And also into like this region as well of the periodic table, again, where you see like tin, antimony, bismuth, lead, even though they're not technically transition metals, all these guys within this sort of area here, they can have a variable charge, which means in certain situations they may be +2, in other situations they may be +3, and so forth. There are 3 exceptions, though, in the transition metal region that also have fixed charges, and that is zinc and cadmium. No matter what the situation is, even though they're transition metals, they will always be +2, and silver will always be +1. So those are sort of 3 exceptions in the transition metal region that have fixed charges. So when we talk about type 1 sort of guys and metals, it's anybody in group 1, anybody in group 2, anybody in group 3 are these 3 red guys here, zinc, cadmium, and silver. Anybody that's type 2 is pretty much all the metals outside of that, the transition metals and so forth. You won't have to worry about carbon having any type of charge or anything like that. You're welcome. It really won't have a charge in that sense. It won't really hook up with a metal or anything like that. So in most cases, so there's really no good pattern on sort of group number 4, and that's because if you look at where kind of group 4 is, up on top, we have carbon, which is a nonmetal, but then we get into some of our semi-metals, and then if you go on the bottom of group 4, it's over this way, you got some actual metals. So there's a lot of all 3 of the types of elements present in that group. So there's really no good pattern. And just so we're clear, when we're talking about -3, -2, -1, it is above the staircase. We're talking about just the non-metals in that case. Most of the time, carbon's going to hook up with other non-metals, not very much with a metal at all, usually. So it's going to hook up with non-metals, and we'll talk about what to do in that situation. You actually don't have to worry about charges. Other questions on that? Okay. So coming back here, when we see iron 3, the good news is it actually tells us what the charge is on it. So iron 3 means I have an iron ion with a +3 charge. You're welcome. Bromide is group 7, which is -1 charge. So when we put these together, again, we always want to equal 0. So we have +3 on the left, -1 on the right. So again, if it's easier for you, you could just draw it. And you can see we need 3 of those guys to balance out the charge, which means the formula should be Br. FeBr3 would be our correct formula. 1 iron with a +3 charge, 3 Brs with a -1 charge each gives us +3, -3, no charge. Same thing here. We see lead Roman numeral 2 automatically tells us we have a lead with a +2 charge because of that. Phosphide is phosphorus on the periodic table, P, which is group number 5, which has a -3 charge. Again, when we put this together, 2 and 3, common number there is 6. So to get my phosphorus to 6, I just need 1 more. To get my lead to 6, I actually need 2 more of those guys. And again, we got +6 on the left, -6 on the right. And we could literally at this point could just write what's there. So I got 3 of these guys and I got 2 of those guys. And we will have the right formula there. Any questions on that one? Here is nickel 4 oxide. Again, same thing when we see that Roman numeral. Tells us what the actual charge is. So that's going to be a +4 because of that. Oxide is oxygen, which is group 6 on the periodic table, and that's going to be a -2. Again, when we put this together to balance it out, we could hopefully see that we need another one of those guys, and that would tell us that it is NiO2 in this case. 1 nickel at +4, 2 oxides at -2 each. Everybody's balanced. Any questions on any of those there? Okay. So those are type 2 Roman numerals needed. Roman numerals are needed to indicate the charge, the positive charge on the metal. And again, the good news is you will always know what the charge is on whatever is bound to it. And to summarize sort of what we were just talking about with the periodic table and stuff, again, type 1 guys are those metals, which are always the important guy when you have a metal and non-metal together. If that metal is in group 1, group 2, group 3 on the periodic table, they have fixed charges, along with zinc, cadmium, and silver, which also have fixed charges. Those guys do not need Roman numerals, and they are type 1 compounds. Now, most of those transition metals, as we talked about, and again, just to the right of the transition metals, when they hook up with non-metals, they will need Roman numerals because they really do have that ability to do multiple types of charges. All right, so let's just try a few more here. Whoa, that is super small. I'm not sure what happened there, but we got MgBr2, we have Li2O, we have CrF2. Go ahead, why don't you take a minute here or so and give us the proper name of each of those, see what you come up with. Okay, so let's take a look. So again, we want to look and identify what we got going on. We got magnesium here, and that's a metal. We got Br, which is a bromine, which is a non-metal. Magnesium's group 2, which means this is a type 1, which means we don't have to worry about anything other than naming it, which means we would use the entire first name there of the metal, and the second name would get the IDE. Also means it has a fixed charge, so we would not need to use any type of Roman numerals in this particular one. Same thing here. If we look at this one, this is Li, which is lithium, which is a metal. O, which is oxygen, which is a non-metal. Lithium, which is group 1 on the periodic table, also means that it has a fixed +1 charge and is type 1, which also means we do not need the Roman numeral here. So this would be lithium oxide. Again, because lithium's group 1, it always, no matter what the situation would be, always going to be +1. Same thing with our magnesium, because it's group 2, no matter what the situation is, always going to be +2 there. Now, if we look at the last one, Cr is chromium, which is a metal. F is fluorine, which is a non-metal. But Cr is found in the transition metal region, which automatically should tell you it is a type 2 compound, which means it can have multiple charges. So we do want to kind of figure that guy out. So chromium could have, a variety of charges. But when we look at the F is group 7, which is a -1 charge. And there are 2 of them, which means we have a grand total of -2. And that means that our chromium here should be +2 to balance it out. So this is going to be chromium, it's getting late. Chromium Roman numeral 2 fluoride. I guess there. Very badly written chromium Roman number 2, but fluoride. Any questions on those guys there? Okay, so remember, always look at the metal. It's either going to have a fixed charge, which means no Roman numerals, or it's going to have a variable charge, which means you do need a Roman numerals. Any questions on type 1 or type 2 compounds there? Okay. Here's just a decision tree to help you decide which way to go. Again, type 1, fixed charge, group 1, 2, 3 on the periodic table, zinc, cadmium, silver. Type 2, transition metal. And as you can see here, transition metal, Roman numeral, non-transition metal, no Roman numeral basically needed. So now we're going to talk about type 3 compounds. Type 3 compounds are a little bit different. Type 3 compounds are binary compounds that contain only nonmetals. So this is when we get two nonmetals together in type 3. As we talked about earlier today, that is a covalent compound. We actually have sharing of electrons happening here. These guys are the simplest to name and do, but I will also say they are the ones people screw up pretty much the most when they go about naming these, and because they think it needs to be harder than it is. I will get rid of that table because it's not table 5.3 in this book, but you do have a similar table in your book of the prefixes. So a lot of times people always want to use prefixes, as I was talking about earlier, when they're naming things, and they want to put it in all the wrong places. But this is actually the place where you should do it when you have a type 3 compound, when you are dealing with two nonmetals. We use prefixes here. So this is definitely the place to use prefixes. Like mono for 1, di for 2, tri for 3, tetra for 4, and so forth. We'll see a chart in just a second here. We basically use the whole name of the first element. And the second element gets basically the nonmetal name with the IDE. The only difference is we use a prefix, perhaps on both names, to indicate how many of each of those elements are present. There are a couple of rules. The first rule is we do not use mono on the first name, but you absolutely can use it on the second name. So mono is never used on the first name, but perfectly fine to do on the second name. And a couple of times when we do get prefixes, like from the prefix, there's like an A at the end of the prefix and an O at the end, at the beginning of the name. We get these kind of two vowels that back up to each other. So we usually will drop an A off the prefix, or sometimes we get two O's that back up to each other. We'll drop one of the O's off. So for example, if I had CO, when I see that, C is carbon, which is a nonmetal. O is oxygen, which is a nonmetal. I should be super happy at this point because I don't have to worry about charges. I don't have to worry about balancing anything. I simply just need to write what's there. I have one carbon. Prefix for carbon is mono, but we do not use it on the first name. So we would just use the whole name of the first guy. Prefix for oxygen here is mono because there's only one. So you may be tempted to write mono and then it becomes oxide. This would be carbon monoxide, and that is not the name. We actually do drop one of the O's off, and this becomes carbon monoxide as the name. So mono, okay, on the second name, not on the first name. When you get a prefix where you have multiple vowels back to back, we typically will drop it, and that usually occurs with an A and O situation, an O and O situation. Oddly, an I and I situation seems to be okay. So that's okay if you kind of have that situation occurs. Let us take a look at these prefixes. Here's the prefixes. Again, di is 2, mono is 1, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8. In case we're going that way, nona is 9, deca is 10. So basically, these guys are really easy. We just need to basically figure out how much is there and, write the appropriate prefix. You don't have to balance things, don't have to worry about charges or anything like that. It literally should take you like a minute to do these or less because there's really nothing to balance or anything like that. So let's take a look at some of those considerations like I mentioned earlier. Again, very common using those prefixes. We do end up with, again, a couple of vowels that back up like we see here. So usually it is the prefix vowel that gets sort of removed, and we end up with monoxide. Some things should still be called by their normal names, like common names, water and ammonia. We also have that CH4 that we had on that list, which is methane. One sort of exception to sort of a non-metal interaction is when you have like hydrogen involved. Hydrogen is a non-metal, Cl is a non-metal, but it's actually not named like non-metals. It's more named like an ionic compound, where we think about hydrogen here as being H plus and Cl minus. So we actually would call that hydrogen chloride. And again, even though they're both non-metals, because it is hydrogen, there's some unusual properties and it's treated a little bit differently. So again, that's one exception as well. If you had HBr, that would be hydrogen bromide. So it's just kind of a different thing. H2S would actually still be hydrogen sulfide, even though there's two of them here. So again, it has more to do with hydrogen than anything else. And that's sort of an exception. We think about hydrogen as being more ionic here when we sort of name it, even though technically it's a non-metal as well. All right, so let's take a look at some here and see how you do. I2O7, CO2. Let's do PCl3. Let's also do dinitrogen pentoxide. Give me the formula of that. Let's do carbon tetrachloride. And let's do dioxygen I'm just making this up, tribromide. Why not? I'm sure that exists, but we'll go with it. All right, guys on the left, let's go with names. Ones on the right, let's go with formulas, which is a non-metal. And at that point, I should be really, really happy because I don't have to worry about charges. I don't have to worry about balancing anything. I really just got to pick the right prefix there. So 2 means di, and we use the full name there of the first element. So it'll be diiodine. 7, the prefix is hepta, and oxygen becomes oxide, and this would be hept oxide. Here we would get that AO combination, and we would want to not have the A in there, and we would want to get rid of it there. Question on that particular one there. Okay, so looking at the next one here, we have C, which is carbon non-metal, O, which is oxygen is a non-metal. So using the first name there of the first element, carbon, prefix would be mono, but we do not use it on the first name. Prefix here would be dioxide. So carbon dioxide, again, don't have to worry about balancing or anything like that. Again, looking here, that is phosphorus, non-metal. Chlorine, non-metal, so same approach. Only one phosphorus, so do not need a prefix here. Whole name of it, prefix for this guy is 3, which is tri. Chlorine gets the IDE treatment at the end, and this would be phosphorus trichloride. Any question on any of those 3? The easiest out of all of them are going to be these guys, because as soon as I see di in that name and penta kind of in that name, I automatically know it's 2 nonmetals, which means, again, I do not have to worry about charges. I simply need to write what it says. So di is 2 and nitrogen is N, so N2. Penta is 5, oxide is oxygen, O5. That's it. Don't have to balance anything, just simply write it out. Carbon with no prefix, but tetra has a prefix. Carbon no prefix means that it really is mono, my prefix, which means I just have one carbon, which is what I should write. Tetra is the prefix for 4. Chloride is Cl, so CCl4. Again, don't have to worry about balancing anything here because there are no charges involved, because they are actually sharing electrons here. So nobody has transferred electrons to become positively charged or negatively charged here. Last one is di, which is 2, tri, which is 3. Again, as soon as I see those prefixes, oxygen is O, di is 2, bromide is Br, tri is 3, and there it is right there would be the correct formula. Like I said, these are really the easiest out of all of them. But to be truthfully honest with you, like I mentioned, they are the ones people really do screw up the most because they want to do some type of balancing, some type of charges and stuff like that. So don't do that. Yes, and you'll be okay. So that's a very good question. And it's actually just what I was about to say. So at this point, we only use prefixes, as you can see here with type 3 compounds, when we have two nonmetals together. That is the only time pretty much that you should use prefixes. We also do not see any Roman numerals used here because Roman numerals are only used for type 2 compounds. And type 1 compounds have neither Roman numerals or prefixes. So if at some point along the way you're finding yourself writing iron, Roman numeral 3, dibromide, and you got prefixes and Roman numerals, you might as well just put an X on it because it is not correct. So absolutely type 3, only place you really should be using prefixes, and type 2, only place you should be using Roman numerals. And again, type 1 should have neither of those two things in there. So everybody, type 1, type 2, type 3, has their own sort of way of naming them and their own sort of way of sort of identifying things as type 1, type 2, type 3. Again, if you see something that's a metal, non-metal with no Roman numeral, you know it's type 1. If you see a metal, non-metal with a Roman numeral, it's type 2. And if you see prefixes, you should know it's type 3 and non-metal, non-metal interaction. Question on that stuff there. It's a good question. Okay, so what I'm going to just mention again, type 1 compounds, always metal and non-metal together. That forms an ionic bond, which is no sharing of electrons, positive, negative attraction together. And again, the important part there is the metal going to be in that group 1, 2, or 3. No need for Roman numerals here. So no Roman numerals, no prefixes here because they have fixed charges. Type 2, also metal and non-metal, also ionic compound, also held together by positive, negative attraction, no sharing of electrons. Type 2 metals, again, are transition metals, but do have a variety of charges, which means they use Roman numerals, but no prefixes. Yeah. And type 3 that we just talked about are covalent compounds, which means they are two nonmetals together. They're going to be sharing electrons, and they use prefixes, but no Roman numerals. Yeah. So again, as we just kind of summarized there, each of these have sort of a distinct way of sort of naming those things. Again, another sort of decision tree to kind of help you decide which way to go. So the last thing we're going to talk about in terms of naming are what are referred to as polyatomic ions. Polyatomic ions are essentially groups of nonmetals. These are groups of nonmetals that are bound together actually through sharing of electrons, and they actually have charges, which is why they're called ions. So you actually have two or more nonmetals together that basically have an overall charge. And although they are ions, they're actually held together as a unit by sharing of electrons. So it's kind of an interesting thing. So a polyatomic ion basically is maybe two polyatomic ions together, maybe one. If we look at something like this NH4NO3, if we actually break this apart right about there, this actually contains two different polyatomic ions. We have on the left-hand side This guy here, which is NH4 plus. And just so we're clear, that one nitrogen and those 4 hydrogens, they're all actually bound together through sharing of electrons. They basically move as one unit, and that entire unit has a +1 charge. It actually looks like this. They are actually sharing electrons with the nitrogen, and that entire thing has a +1 charge. That's why it's an ion, but it's actually sharing electrons here, which is what kind of makes it interesting. This is nitrate, and that is NO3 minus, that one nitrogen and 3 oxygens, just like the other guy, is sharing electrons. They are bound together, and the entire thing has a -1 charge. That is why when we put this together, this essentially has a +1 charge. It has a -1 charge. So when we put them together, we actually just need one of each. So just like an ionic compound, we actually, in this case, just need one of each. Each of these guys have a special name. NH4 plus is what is known as the ammonium ion, not to be confused with the ammonia ion, or the ammonia, but ammonium ion. NO3 minus is the nitrate ion, which means when we go to name this, we actually just put both names together. This is what is known as ammonium for the first guy and nitrate for the second guy. Most polyatomic ions are actually negatively charged. This is one of the few positively charged polyatomic ions. Now, because most of the polyatomic ions are negatively charged, polyatomic ions find themselves attached to metals a lot. So because, again, like most of them are negatively charged, they attach themselves to these positively charged metals. And what that means is when we go to name a polyatomic ion that's attached to a metal, it will either be attached to a type 1 metal, where just like what we do with a type 1 compound, we would use the whole name of the metal, and we would use the name of the polyatomic ion. Again, the polyatomic ion here would be the negative ion, the metal would be the positive ion. If we had a type 2 metal, like we were talking about earlier, our transition metals and such, we would do the same thing as we did earlier. We would use the whole name of the metal. We would also use a Roman numeral to indicate the charge on the metal, and we would use the whole name of the polyatomic ion. Again, the polyatomic ion being negative, the metal being positive. So, like I said, probably 98% of the time, you're going to come across a polyatomic ion that's negatively charged, and you're going to come across a polyatomic ion that's attached to a metal. And you basically would handle them just like type 1 or type 2 compounds that we just talked about. And we use really the whole name of the polyatomic ion when we do that. Here is a chart from your book of some polyatomic ions. The good, bad news is, you just got to memorize these things, the formulas and the names. So there are ways that you can sort of help yourself memorize names. If you look at this chart, and we'll see another chart as well. For example, if we look at something like NO3 minus, again, the 1 nitrogen and 3 oxygens are all together, has a -1 charge. That is what is known, as I just wrote, as the nitrate ion. If you take NO2 minus, 1 nitrogen and 2 oxygens, also has a -1 charge. That is what is known as nitrite, ITE. If you look on that chart where sulfur is, we have SO4 2 minus, 1 sulfur, 4 oxygens are all together as a unit. They will never break apart into individual elements. Has a -2 charge. That is what is known as sulfate. We take something like SO3 2 minus, 1 sulfur, 3 oxygens all together, has a -2 charge. That is what is known as sulfite. What is the difference between these two guys? They both have a -1 charge. They both have nitrogens. The difference is the number of oxygens. So in this group of two guys that are related to each other, the one with the most oxygens ends in 8. The one with the least oxygens ends in 8. So usually the most oxygens in a group of 2 ends in 8. The least oxygens ends in 8. Same thing down here. Difference between these two, both have a -2 charge, both have a sulfur. One has 4 oxygens, one has 3 oxygens. The one with 4 oxygens ends in 8. The one with 3 oxygens ends in 8. So that's a good way to group things together. Sometimes people will remember all the 8s and know that the ites are just 1 oxygen left, or vice versa. You could learn all the ites and know that the 8s have 1 more oxygen, nothing else changes. There's also some other things that we sometimes will see here. For example, in this region, if we look at CO3 2 minus, again, 1 carbon, 3 oxygens all together with a -2 charge. That is what is known as carbonate. If we put an H plus in front of it, not just an H, but actually an H plus, we get HCO3 minus. That is 1 hydrogen and 1 carbon and 3 oxygens all together, has a -1 charge. We basically put a hydrogen in front of it. We call this hydrogen carbonate. And this is sometimes called bicarbonate, kind of an old name. Like when you have heartburn right about now, some bicarbonate might help you. And that's a very common sort of way. We see that also here. That's hydrogen sulfate or bisulfate is a very common sort of way of doing that. Now, there's also sometimes groups of 4 that are related to each other. The most common group of 4 is what we see up here on the table. I think it's right around here in this area. And that is our ClO4 minus, our ClO3 minus, our ClO2 minus, and our ClO minus. Every single one of these guys has a -1 charge. The only difference between every single one is the number of oxygens that are involved. In a group of 4, you could kind of split it up right there in the middle. To the left-hand side, these guys have the most oxygens, which means they should end in ATE. So that would be chlorate. That would be chlorate. Clearly, you cannot have the same name for 2 things that are different. So the one in a group of 4 that has the most oxygens, in addition to ending in 8, it actually starts with per in front. And that is why that is referred to as perchlorate. Chlorate, the 2 on the right have the least number of oxygens in a group of 4. They would end it with ITE. So that is chlorite. And the guy to the far right would also be chlorite. Same idea here. We cannot have, obviously, the same name for 2 different things. So in a group of 4, if it has the least number of oxygens, it will start with hypo and end in ite. So we have perchlorate, chlorate, chlorite, and hypochlorite. And again, in a group of 4, that's where we have those additional parts of the name that come before. You could also, if you wanted to, Cl is chlorine, and that's group 7 on the periodic table. You could swap out anybody from group 7 in there. So if you had something like this guy, instead of it being chlorate, that is now bromine, this would be bromate. So again, they're sort of interchangeable there with those halogens. Now, a vast majority of everybody on this polyatomic ion table ends in either ate or ite. There are some that do not. The most common one is like right here. That is OH minus. That is hydroxide, IDE. There's also cyanide here, which is right there. Ends in IDE. But most of them will end in either ate or ite, but some will end in IDE. But again, a majority of them will end in that ate or ite. Any questions on that? Again, unfortunately, memorization is what you got to do with these guys, formulas and charges, and also names so that you can put them together sort of properly here. So let's take a look at some examples, how we go about naming it. I'll just use this one. It's another table similar to the one you have, but we'll use it so it's not as written on. You could kind of still see some of the names here. So why don't you, let's see here. Why don't you come up with the name for NaNO3, see what you come up with. Why don't you do Ca, let's do CaOH2. Let us do FePO4. So see what you come up with in terms of those names. And I'll do some names and we'll go to formulas. So let's do on this side, let's do copper, Roman numeral 2, sulfate. Let's do magnesium, hydrogen, carbonate, and let's do potassium. Let's do potassium cyanide. All right, why don't you take a few minutes here and see what you come up with. Let's take a look. So again, here we see Na, which is sodium, and that is a metal. And we see NO3, which hopefully at some point you will recognize as a polyatomic ion. And again, here, whenever we got a metal sort of involved, as we talked about before, it's sort of the important guy. So because this metal is sodium, it's really a type 1 metal, which means, as we've talked about, does not need a charge or anything like that. So we basically just need to use the whole name there of the metal. We could recognize this hopefully as NO3 minus from the chart, which the name of that guy is nitrate. And we would simply just put nitrate there. And this would be sodium nitrate. It's NO3 minus, and that's because sodium has a +1 charge. +1, -1 needs one of each of them. Any questions on that one? Again, looking at the next one, we have Ca, which is calcium, also a metal, which means it's probably important. Inside the parentheses here, we have OH, which hopefully you will recognize when you learn these guys, that OH is OH minus, which is hydroxide, which is a polyatomic ion. We know that calcium is group 2, which means it has a +2 charge and is type 1, which means we simply need to use the whole name of that metal. No Roman numerals needed for it because it's calcium. And we would use the whole name of the polyatomic ion, which is hydroxide. Again, here, much like everything else we've been doing up until this point, even though there are 2 hydroxides there, it has no effect on the name. So this again should be calcium hydroxide, not calcium dihydroxide or anything like that. Again, no use of prefix. unless the polyatomic ion itself has a prefix. But if it doesn't, then you should not put an extra one in there. Let's talk a little bit about the formula here, though. We have calcium basically here, and we're putting hydroxide together. So again, we have +2 and -1. So we really do need 2 of these guys to balance out the charge. That would give us a -2 charge. That is a +2 charge. So when we write a formula like that, if we just wrote it like this with no parentheses, that would imply that we have 1 calcium, 1 oxygen, and 2 hydrogens, which is really not the case because, as you see here, we have 2 oxygens and 2 hydrogens. So whenever you have more than one polyatomic ion present, you need to put parentheses around the polyatomic ion and the number on the bottom for how many you have. So whenever you have more than one, you need to put parentheses around that polyatomic ion and a little subscript to the bottom to indicate that, so you don't get a weird formula of something you're not intending to write. Question on that there. We look at FePO4, we would break it right about there. Here again, a metal. The PO4, hopefully again, you will be eventually able to recognize that as PO4 3-, which is our phosphate here. This metal, though, is a type 2 metal, which means we do need a Roman numeral happening here. So because we know that the other guy is phosphate, we take the same approach. Because it's phosphate, that 1 phosphorus and 4 oxygens are all going to be together. Has a -3 charge overall, which means the charge on the iron should be +3. And since it is a type 2, we do need to include that in the name. This would be iron Roman numeral 3 for the charge. And again, here we just use the entire name of the polyatomic ion, which is phosphate. Any question on that particular name there? All right, so that is how we get to names. Let's talk about formulas here. So when we have the name and we want to write the formula, just like we did earlier, we want to just basically take all the individual components and put them together correctly. So cobalt Roman numeral 3 means I have a cobalt that has a +3 charge. Nitrate, again, I could go to my table here once I learn it and know that it is NO3-. Again, remembering that this entire thing is 1 unit with a -1 charge. What that means is to balance out the charge, you need 1 more, and you need 1 more of those guys. That gives you a -3 to balance out the +3 here. And now we can put our formula together, CONO33. Again, this would not be right because that implies we have 33 oxygens, which clearly we don't, and 1 nitrogen. A reminder again, we do need the parentheses around it to indicate that we have 3 of the nitrate units and not 33 oxygens. Question on that one there. Copper Roman numeral 2 means we have a copper with a +2 charge, again, because of the Roman numeral. Sulfate right there, that is SO4 2-. Again, here, this entire thing has a -2 charge. Copper's got a +2 charge. We're good to go in this case. That's +2 -2. You just need 1 of each of those. No need for parentheses here because there's only 1 sulfate, and you can just write CuSO4. Question on that one? Coming down here to magnesium. Magnesium is group number 2, which means it does have a +2 charge. Hydrogen carbonate is a polyatomic ion. also known as bicarbonate. Where'd that guy go? Up here. So this right here is bicarbonate or hydrogen carbonate, HCO3 minus. Again, that is 1 unit. It has a -1 charge. I'm going to put it together with something with a +2 charge, which means I need one more of these guys to do that correctly. And again, now I'm ready to write my formula. I'm just going to write it in the center here. Magnesium, I need parentheses because I have more than one of these guys. And I need to put on the bottom how many I have, which would be 2 in this case, 1 here and 2 there. Question on that. Lastly, we have potassium cyanide. Potassium is group 1, which is +1. Cyanide is on here, I think. There it is. And that is Cn minus. Again, in this case, that is all together with a -1 charge, +1 charge. Just need to put them together. KCN. Any questions on how to deal with polyatomic ions? You do have to kind of, learn the formulas and the names and the charges so you can put them together. But as you hopefully can see in these examples, a lot of times they will be basically combined with a metal. So we do fall back to sort of type 1 and type 2 rules with that metal. And again, we use the whole name of the polyatomic ion. It doesn't matter if there's more than one of them in terms of naming, just the name of it. Does matter though when we write the formula, if there's more than one, we do need to put those parentheses and the number on the bottom. Any questions on any of those there? Okay, so let's see here. Just another table in case you don't like the first two, I suppose. So we talked about this, but I'll just scroll it on the screen in case later you want to look at it again. But this is what we talked about in terms of a group of 4. We add that per before. The one with the most oxygens, ends with 8. And we do hypo for the one with the least number of oxygens, and it ends in ite. And again, we could kind of swap it out for other similar guys, and we could put a hydrogen in front. We get hydrogen carbonate or hydrogen sulfate. Again, that hydrogen is sometimes replaced by the word bisulfate or bicarbonate instead of hydrogen. And again, this is sort of a decision tree as to what to name and stuff like that. Any questions on nomenclature, anything we